So thank you very much for joining us today for today's session of the Computational Social Science online seminar series organized by our research center. And it's a great pleasure to introduce our speaker today, Professor Albert Ali Salah. Thank you very much, Hocam. Professor Salah is a professor and chair of social and affective computing in the Department of Information and Computing Sciences at Utrecht. He received his PhD from Boğaziçi University in 2007. And over the course of his career, he has worked at several distinguished institutions, including CWI, University of Amsterdam, Nagoya University, Boğaziçi University, before founding the Social and Affective Computing Group at Utrecht. He is a senior member of both IEEE and ICM, and a research affiliate at DataPop Alliance. Professor Salah's work, as you all know, it's very interdisciplinary. Therefore, it would not be wrong to call him a computational social scientist as well, Ajam. But at the core, he focuses on the use of pattern recognition and machine learning for the analysis of human behavior. And that includes individual behavior, like facial expression and analysis, dyadic and group interactions, and computational social science, most relevant to our work, and especially focusing on migration and mobility through the use of mobile phone data. And today, Professor Salah will present Big Data for Social Good, mobile phone data for migration and mobility. And in this talk, he will discuss how mobile phone data can be used to better understand migration patterns and human mobility, and how big data can contribute to addressing important social challenges. And we are delighted to have him with us today. Thank you very much for joining us. Floor is yours, Hocam.
Thank you very much, Erdem Hocam, for the introduction. It's a delight to meet the students of the program. So basically, as Erdem Hoca said, my group is working on the computer analysis of human behavior. And so the typical pipeline of this is that we sense the human behavior with some sort of sensing, and then we do some sort of analysis, and then whatever we find, we plug into applications. And if you look into these boxes, the sensing can be in real world. We can sense the behavior of humans with cameras, microphones, Internet of Things sensors, but also with mobile phones, because everybody's carrying one these days. But we can also look at the digital world behavior, right? We can look at the digital breadcrumbs you leave behind on the internet. We can look at your activities on online games and social media. And then once we collect the data from the humans, well, we have theory-driven analysis and data-driven analysis, and they are complementary in certain ways. There are a lot of theories of human behavior in psychology, in cognitive science, in sociology. I try to imagine these as different lenses to look into human behavior, right? So psychology looks maybe at individuals or dyads, but sociology looks at masses more, perhaps at a larger scale. If you don't have any theories, if you don't know what you're doing, then you can always do pattern recognition, machine learning, and let the data tell you a story. And maybe you can formulate some hypotheses and some theories through that and then loop back. So this is, no research is purely theory or purely data driven. It's always somewhere in between of different amounts. And then the applications are many. But my group is particularly working on a range of these behaviors that are focusing on the individual, especially sentiment and affect analysis, facial expressions, affect in speech, affect in text generated, for example, in social media. And a lot of this is related to mental health care scenarios. But we're also looking at dyadic and group behavior. So dyads are like two people groups. And if it's more than three people, we usually call it a group. And there you have interaction behaviors like turn taking, mimicry, nonverbal exchange of social signals. And we particularly look at child-parent interactions and patient-doctor interactions. It's basically an extension of the individual behavior analysis. But when we go to the largest scale of human behavior, that's when we start really doing the computational social science, where we look at, instead of 2 or 3 people, we look at 1 million people. Then we use different kinds of analysis. And for us, migration and mobility has been the primary application area, and a little bit of urban computing as well. Now, in this kind of setting, we have 2 challenges. One of them is a technical challenge. How should we create models to automatically interpret and predict complex human behavior? That's the one challenge, and that's a technical challenge. And it has technical difficulties. Like if you have a camera, then how do you clean your data? How do you deal with tracking? If you have mobile phones, we're going to have other challenges. I'm going to talk about them in a minute. But there is also a human challenge or a humanity challenge, because whenever you create a system, there are social implications and ethical considerations, especially when somebody else deploys your system with other purposes in mind. So you can create a face analysis system to facilitate identification to facilities like biometric identification, but it can be easily converted into a surveillance tool and used to oppress people. So the dual use is a big issue in creating technologies. And these 2 things we need to balance if we want to really develop AI that is going to interface with human behavior. Now, one framework that I'm sure all of you are very familiar with is the Sustainable Development Goals of the United Nations, the 17 goals. And we're nowhere near reaching our aims in any of these goals, but at least there is a lot of activity, let's say, in each of these areas at the moment. Now, in 2018, McKinsey surveyed the field of AI and looked at the different domains where AI is used for social good. And some of these map to the Sustainable Development Goals. And you can see, for example, they found 28 studies dealing with health and hunger, 21 studies on climate change, animal and plant conservation, and environment in general, and some other projects on crisis response, security and justice, public and social sector, and infrastructure. Now, that report was updated in 2024, and they have gone now up to 600 case studies. And a lot of them also have actual deployments. So if you look at the number of cases, I don't know whether it's big enough for you to see it, but I can share the slides with you afterwards if there is a need for that. For example, in Sustainable Development Goal 3, Good Health and Well-being, there are 165 AI usage cases, and number of cases with at least 1 deployment, and 23 were 128. So there are also a lot of systems that go into production or deployment. Now, what do we need for doing AI for social good? Well, you first need a problem to solve, such as, improving water quality, tracking species, helping refugees, diagnosing tumors, whatever your problem is. You take the problem, and then you start working together with some partners who already have competence in this problem. Then you need some data to represent the problem. Hopefully you can get also labeling so that you can do supervised learning on it. And then maybe you also have some privacy concerns. So maybe you will need federated learning or differential privacy approaches to decently process this data. Then you're going to need computing power, training systems, doing inference, developing algorithms, testing whether the algorithms are working as good as they work. And then you're going to go out in the real world, and you would need scalable solutions to deploy these in the real world. So I'm going to show you, for example, a bunch of migration related research using mobile phone data. But if you want to do a real world deployment, there needs to be a system which constantly processes this mobile phone data, and the outputs should go constantly to some governmental institutions, IGOs, NGOs, or to some target who can actually use this information to improve the situation with whatever problems that you're trying to solve. Now, one important concept that you need to know is the data collaboratives concept. And this is about cooperation between the private and public sectors in the field of data sharing and statistics. Why? Because most of the valuable data sets are in the hands of private companies. The companies give you services, and by agreeing to use these services, you usually agree that the company possesses your data. So your phone company, for example, knows where you are at almost all the time. So your social media companies that you're using with, they know your preferences, they know your opinions, they know your maybe family photographs. They have access to a lot of information about you. So how can the public sector leverage this data for some public good? Well, that requires a cooperation between the private and public sectors, and that we call data collaboratives. There are ranges of private data. Mobile phone data is not, of course, the only one. You can get private data from satellite images, which can be extremely high resolution these days. You can get social media content. You can have wearables and smartwatches carried by people collecting data. You can get data from infrastructure usage. So every time you use your Akbil in Istanbul, for example, there's a record registered. So they can actually, the municipality may know where you are. Massively played online games, they have very interesting data collection capabilities. So any data trace on systems used by thousands of people can be a source of private data. So I'm going to be focusing on mobile phone data, and even that comes in multiple flavors. How can we use the mobile phone data? The easiest way is if you have an application that people are using, and by signing the informed consent or the agreement, usage agreement of the application, they grant you to use any information accumulated in this application. Now, what kind of data the application can collect, that's contestable. An application may know your GPS location, for example, but maybe if it doesn't do anything with this location, then it may be forbidden for such an application to collect your GPS. So you may refuse that kind of information to the application. So there's always the legitimate interest in collecting some sort of data from the user. But if you can do that, then you can get very detailed data from people who are actually using your application. There are, of course, problems. Usually you get the data only when the application is up and running. And of course, not everybody in a population will use your application, so you will get a sample, and that comes with its own biases. The second possibility is if there is an application on the phone that can interact with a system. For example, if you have a supermarket application and that talks to the beacons in the supermarket through a Bluetooth connection, every time you enter the supermarket, your application may tell the supermarket owner that you're in the supermarket. And then that can be linked to your shopping lists or preferences or wish lists or whatever. And then you can have mobile call detail records or extended data records. So these are interesting data pieces that are stored directly by the telecom company. Now, the first study that popularized mobile phone data for observing behavior was the MIT reality mining study. That was by Eagle and Pentland. And what they did was they distributed 100 Nokia smartphones to people on MIT campus, students and faculty members. And they kept their phone on them for something like 150 days. And a lot of data was collected, basically the locations, call and SMS logs, and the Bluetooth devices in proximity. And then they tried to see what can this data predict. And it turns out that it can predict quite a bit of things. It could predict, for example, whether you were a senior student or a junior student or a faculty member, whether you're an engineering student or an economics student. The behaviors were quite detailed in separating people. From those time onwards, there were a bunch of smartphone-based data collection campaigns. You can see a bunch of them here. And the number of people involved in these studies ranged, from 25 to 20,000. So quite a bit of data was collected. Now, recently we published a survey on using mobile phone data for anticipating displacement. And we kind of mapped the pipeline of how to use mobile phone data in this survey. So this is a figure directly from this paper. And this pipeline starts with your mobile data acquisition, getting your data maybe from telecom operators, maybe from application owners, or sometimes from business to business companies. So I'm going to show you one slide later that we used some airtime top-up data. This is basically when you use your own telecoms credits to top up the phone of someone in a different country. Maybe your mother lives in a different country and you send them top up credits through your phone. That's a business to business model, and it generates very interesting perspectives into migration. Okay, you collect the data, you anonymize and do your aggregation so that usually we want the data to be completely anonymous so that we don't look at individuals. We respect their privacy, but we can generate general insights, like higher level insights at the group level. We collect features and indicators, and then we have statistical models, simulations, and machine learning models to do the analysis. And this can be basically either ex ante, so we can look at forecasting, modeling existing data, agent-based modeling, for example, or ex post, where we try to do descriptive analysis, try to understand what has happened, causal analysis, so which factors caused which consequences, and again, predictive analysis, and nowcasting. Nowcasting is when you are trying to predict data as it flows on a very short time horizon. Now, an example of this was the use of mobile phone data during COVID-19. If you will remember, a lot of effort was spent to implement policies in COVID-19. For example, quarantining, and if you have been exposed to a person that had the virus. This was, of course, before we had the vaccines, but so there were a bunch of applications using mobile phones to combat COVID-19. So situational awareness, trying to understand mobility flows, hotspots of the virus, entry points, travel and interaction patterns. Also predictive analysis. So under different scenarios, how will the disease spread? What kind of measures would help us contain the virus? Cause and effect studies, and also impact studies. Now, for our research, particularly important has been the mobile call detail records, also called CDR. Now, what CDR is, whenever you make a phone call or send an SMS message, in your telecom operator, there is a database and your call is registered there with some fields. So for example, it may have the time of origin, so at what time you're doing the phone call, from which number to which other number, from which geological area to which other geological area. So this we know from the connecting base towers location. And then we can have additional flags, like if there is data transfer, we can have the amount of data transferred, or call duration can be included, and these kind of things. Now, for every single call and SMS, your mobile operator has a line of this. And what can they do with this? Well, they can look at the consumption patterns, they can look at your social network, and they can look at the mobility, right? They can determine your radius of gyration, which means if I place your mobility on a map, what kind of footprint do you have on the map? And this is very interesting because it's correlated with your wealth. If you're a rich person, then your radius of gyration is typically larger because you have means to travel. Of course, these are not one-to-one mappings, but if you accumulate enough of these indicators, you can actually get a pretty good picture of what's happening. Joshua Blumenstock from Berkeley did a famous study where he used mobile call detail records, and he was able to predict the wealth distribution in Rwanda with a $15,000 budget, rivaling the accuracy of the national census, which has usually a couple of $1 million budget. So the mobile call data records or detail records, what are the advantages? Well, it's very comprehensive. It can contain all the people in a country. Well, usually not all the people, depending on the country. For example, if you do this in Turkey, we have 3 major telco operators, each of which has roughly 30% of the market share. But in Ivory Coast, for example, Orange Telecom in 2012 had 96% of the market share. So you could actually have a very, very comprehensive data set. And in Turkey, even 30% is still millions of people. You might not need explicit consent depending on what kind of analysis you're performing. So if you have a telecom agreement in Turkey, for example, your user agreement includes the condition that your data may be used anonymously for research purposes. So, and it can also be quite granular. The disadvantages are that this kind of data are very difficult to obtain. You need to work with a telco, and you need to basically limit the analysis to both whatever your purpose is and to a certain time. And after the time limit expires, you should destroy the data. So it's kind of like it's difficult to gain access and sustain access to this kind of data sets. It is sensitive. If you do not anonymize this kind of data properly, it can lead to a massive surveillance scenario. If you really need to obtain consent, it's difficult, but it's not impossible. So Blumenstock, for example, sent the users of the data SMS messages because he was working with the telco. And people who responded and gave explicit consent to the SMS messages, then they received a different survey, and they kind of, their personal information was linked to the mobile phone data, but only when they gave the consent for it. Now, the first data set that made public CDR data was from Ivory Coast. Orange Telecom did it from 5 million people collected over a year. A very interesting data set. We, with a master's student, Didam, we participated in that data challenge back then. And later in 2013, they made a second run from data from Senegal because it was a very successful challenge. Then in Italy, Bruno Lepri and colleagues organized the Telecom Italia challenge. And then there was a Telefonica challenge organized by Nuria Oliver in London metropolitan area. And we organized in Turkey the Data for Refugees project with Türk Telekom, Boğaziçi University, and TÜBİTAK between 2016 and 19, actually. And we made data from 1 million users of Türk Telekom available to researchers as a data challenge. And there were many groups participating in the data challenge, including one group from Koç University, another from Sabancı, and also a lot of foreign groups. I'm going to show you a couple of results from the challenge in a minute. Later, we had the European project Hummingbird, and that project was completed recently. And in Hummingbird, we used data from Turkcell, from 5 million people, and we studied mobility within Turkey and also mobility from Turkey to Europe, for example. Now, let me stop for a moment to see whether there are any questions from the audience so far. I don't see anything, so I'll just continue. Okay. So Data for Development was, as I said, the first big data challenge. And what they did was they created a special ethics committee for this. And you would apply with a project proposal, and they would evaluate the proposal if they liked the proposal and if they thought that you could actually technically do this kind of research, then they would grant you access to the data set. So out of roughly 300 applications, only 150 of them received the data set, so roughly half. And then the participants were tasked with destroying their copy after the challenge. What did they offer? Well, they offered antenna-to-antenna traffic on an hourly basis. So this is like saying, okay, on this day, between 1 o'clock and 2 o'clock, between Taksim and Kadıköy, there were 250 calls. What does that tell us? Well, it tells us that at least 250 people were, or, if these were unique numbers, obviously, 250 people were at that location at that time slot. And that tells you actually how a city is used. For example, if a traffic is in an area is quite high in the late hours, maybe let's say after midnight, then you can guess that it's an entertainment area where people go and stay late. Other areas, for example, with traffic during work hours, well, you can guess that there are businesses in that area. So this gives kind of like a pulse of the city. It helps you to understand what's happening in a city. They also enabled two different types of trajectory informations. One of them called fine-grained, the other one called coarse-grained. The fine-grained is collected from 50,000 customers for 2 weeks at a time. And then for every customer, you have the precise antenna information, location information. So let's say you have me in the data set, in the fine-grained. You know exactly which antennas I'm calling from for all this 2 weeks. You don't know my actual number. A random number is generated for me. And then I am dropped back into the bag, and then another 50,000 customers is drawn. So if you have me, let's say for 4 weeks, let's say 2 weeks consecutively in 2 slots, you don't know that I am the same person. This way, they help the systems so that the people cannot be tracked over longer periods and they cannot be identified. And then you have the coarse-grained, where you have a customer tracked for the entire year, but then the location information is much coarser. It's just sub-prefecture. So I say, for example, this person is in Beyoğlu, okay, not in this base tower, near this base tower, but basically what I'm saying is it's such a coarse level that it's impossible to identify that person precisely. But you need this kind of information if you want to see internal migration, because you want to see whether someone goes from Istanbul to Ankara and stays there for 6 months, so that you can say, oh, this person immigrated from Istanbul to Ankara. So that's an internal mobility issue. Now, aggregation and anonymization are very important. What we do is we aggregate both spatially and temporally. So instead of giving the call precise time and location of the calls, we give them in 1 or 2 hour slots and then we aggregate the locations into these cells, what we call Voronoi cells. Each Voronoi cell is basically the locations that are nearest to the central base tower. And if in the city centers, in urban cities, there may be many cell towers, so these Voronoi cells may be very small. In that case, we merge them so that, again, the privacy can be preserved. Now, in the Data for Refugees challenge...
Hocam,
Yes.
Albert Hocam, can I ask you a question?
Sure.
So the data in terms of this high granularity is already out there. And what I understand is that what you are trying to do is to aggregate it, to decrease the granularity, to ensure privacy protection.
Well, it's not exactly out there. The data is in the hands of the telco. What we do is we do the anonymization and aggregation within the telco and only take out sufficiently aggregated and anonymized data.
Okay, so when you have the data,
it's already aggregated.
It's already aggregated.
Of course. Yes. Thank you. This is a good question. I will describe a little how we do the processing in a minute. But I want to add here that in the Data for Refugees challenge, we just followed the process that was introduced in the Data for Development challenges, but with one distinction. Because Türk Telekom knew whether the people were registered with Syrian passports or the ID numbers given to Syrian refugees by the Turkish government, or whether they purchased a subsidized refugee tariff, we were able to tag every CDR with refugee and non-refugee tags. That helped us to do differential analysis between the refugee population and the local population. We've had 5 priority questions like safety, health, education, unemployment, and social integration. And our aim was to improve the conditions of life for the refugees in Turkey. Every project had to be under a strict agreement to protect the data confidentiality. We only admitted the proposals that had enough technical details. Projects with commercial interests, with poor technical description, with sensitive topics were all denied. So, for example, we received projects from ministries of defense of several countries, including the Turkish and the American ministries of defense. Those were not granted the data. Now, there are a bunch of ethics issues. The consent has to be obtained. The data sharing should be permitted by the owners. That was guaranteed by the Türk Telekom user agreement. We had to ensure that there is protection of individuals. You cannot track any specific individuals or you cannot identify them with this data. The data that comes out of the telco has to satisfy these requirements. There is limited use of data. At the end of the project, after a certain grace period, you have to destroy it. And we follow a do no harm principle. So every report is screened and you cannot publish any project reports that might harm the refugees. For example, you cannot say, oh, in this region, there is an increased refugee presence and there is increased criminal activity, implying that they may be involved in criminal activities, for example. Of course, correlation is not causation, but sometimes an incorrect formulation may be harmful. So we were preventing these kind of effects. There were also very specifically, for example, during the tourism season, the Syrian refugees were forbidden from working in Antalya by declaration of the governor. But on the data set, we could see that they were working. So it was impossible to publish this officially, because if there was a backlash, these people could have lost their livelihoods. So one thing also we do is we process the data, we open the data 6 months after its collection. That is enough buffer so that, for example, there can be no action taken on irregular migration routes, for example. There's no personal information, no profiling, clear legal agreement, and data protection by design and default. This is the question that Erdem Hoca asked. Anonymization is done during the data collection so that when the data is out there, even if it is leaked, it cannot be used for harming people because you cannot actually locate any person specifically in the data. Okay, what did people do with this data? Well, they looked at mobility between different locations. This was from the Koch group, from Mirai Koch group. They looked at the mobility of seasonal workers. For example, the Syrian refugees were granted working permits for the hazelnut harvest. But where will they come from? How many will they will come? Where will they stay for the harvest? And where will they? When will they return? These were all question marks, and the data all tells you all of these in a very nice way. This was a collaboration between Sabancı and MIT. Social integration indicators of different cities. So for every city, they looked at relative refugee to local calls, to locations where refugees and locals are encountering each other, spatial integration and employment scores, and they generate a single index that tells us how integrated is this city. And they used 2017 data and showed, for example, Urfa had a very poor score. And sure enough, in 2018, there were violence against refugees in Urfa. Again, it tells you that these kind of indicators can help you shape policies to improve things in these cities. This was a project done by Kızılay. They looked at refugee concentration in Istanbul. So these colors show you where the Syrian refugees are. And the red dots are mobile health centers that had Arabic translation capabilities. So you can see, for example, this mobile health center is placed in an area where there is not much refugee concentration. And in these areas, there is a concentration, but there are no mobile health centers. Of course, when you try to translate this to policy, it's not so easy as saying, oh, let's take this dot and move it there, because maybe there is a hospital here where it's supplying the doctors here, etc. So there may be other factors that you need to consider, but it actually gives you a good visualization of what's the situation. This is an Italian group doing measles simulations, because most of the Syrians were not vaccinated against measles, whereas the Turkish people were. And they showed through simulation that in cities that were well integrated, actually a possible epidemic would spread much more slowly, because the Turkish people coming into contact with the Syrians would act as a buffer. Other projects, from the Data for Development Challenge, also mobility on special days, people's behavior during emergencies. This was our project in Data for Development, anomalous event detection. So this was a single base tower, and this heartbeat is basically the number of calls per hour. So you can see that it is showing the activity at that location. And all of a sudden, on 2 consecutive days, you have this peak activity. And then you can say, okay, what happened during those days so that people are calling each other? And then you need to, well, what we did was we cross-checked newspapers or news sources to identify what was happening at that location at that day and time. All the reports of the Data for Refugees study are collected into a book, the revised reports, but the initial reports are obtainable from my website. They're openly available, and you can get them and read them. Now, the policy implications is that basically you need to take into account a large number of factors when you actually want to influence policy. Now, mobile phone data is nice, but it's very reductionistic. You cannot reduce everything to a single or a few numbers. You have to take into account the actual conditions. You have to take the risks with the dual uses of technology into account. And you have to also think about algorithmic biases and data biases. Now, in the Hummingbird project, our aim was mapping and understanding of migration flows. This was a Horizon project that ended in 2024. We get data from Turkcell this time, and we looked at refugees in Turkey, Syrian and Afghans, migrants and other migrant groups. And then we did a bunch of different analysis based on this data. We had migrant population mapping, so we looked at where the migrants are, combining this with land cover and satellite information. We also looked at specific events. For example, in March 2020, when Recep Tayyip Erdogan announced that he's opening the borders to Europe and he's releasing the migrants, the refugees into Europe, we actually can see in our data set who went to the border during that time and who disappears from our data set and who goes back to their origin after the borders are closed again. And our analysis shows that the people who actually crossed into Europe were not the Syrian refugees, but they were mostly Turkish citizens that were probably politically in trouble at that time. If you remember the political situation in 2020. And those are the people who actually went into Europe at that time. We also looked at post-earthquake mobility analysis after the Hatay earthquakes. And there we collaborated with sociologists from Galatasaray University, which we actually initially made contact after a talk at Koç University, where we presented our initial results with the mobile phone data analysis. And this study came in EPG Data Science last year, where we looked at what happened after the earthquake to the local Turkish and Syrian population. And we saw that the Syrian population actually had to go, for example, to the refugee camps, whereas the locals, they had connections all over Turkey and they were able to travel far, for example, to Istanbul, to Ankara, to bigger cities, and they had an easier time. So as we guessed, it was a kind of intersectionality where the already fragile refugee population was much more severely affected by the earthquake. I also want to show you this slide from a completely different data source, also within the Hummingbird project, but there we worked with DT1, which was a top-up transfer company. So here you can see on the left, the mobile top-up transfers from Italy to Cameroon. And here on the right, you can see the normalized official migrant stocks of Cameroonian migrants living in Italy. And you can see that a lot of Cameroonian migrants apparently are sending mobile remittances to their families in Cameroon, and their presence can be detected with the airtime top-up transfer data. And the official data does not show any activity or very little activity in Sicily, whereas from the top-up flow data, we can see that there are many Cameroonian migrants in Sicily area and in Bari areas. Our latest book was Data Science for Migration and Mobility, which was published by Oxford University Press under British Academy series. That is more of a textbook and tries to explain what kind of data sources can we use for migration and mobility, and how do we incorporate them, how do we group them together, what are the applications. This slide I just added before the beginning of the presentation. We have a new project starting in the Netherlands called Decide, Democratizing AI, Empowering Citizens Through Transparent Decision Making. It's a big NVA org project with maybe 30-40 partners. And at the moment, it's hiring a lot of PhDs and postdocs all over the Netherlands. And if you're looking for a PhD position or a postdoc position in the Netherlands, this website actually is the one that is used by all universities in the Netherlands. So all academic positions are also announced on this website. So this is probably the best place to start your search. let me stop here and get questions. You can always write to me afterwards, an email, or connect with me on Twitter or Blue Sky. And thank you very much.